got lots of things you liked. I'm quite happy about that. I was happy to see that quite a few of you explicitly commented that you liked this exposition to the associative scan, this faster way of working through a prefix sum. I wasn't sure whether that would be popular or not, so that's good to hear. And then there were a few content questions. So let me see whether I can pick out something specific. Okay, I'll do some of the questions about theory again by repeating things today a little bit. There are some questions about the big picture and some about the math and the names. So maybe let me start with this question: why are they called filters? Why is it called filtering and smoothing? So maybe those of you who are electronics people have actually seen that you can buy filters online if you like. They're really cheap. Here is one for 99 cents. That's where this name originally comes from. They are when radios became a thing, when sending signals through wires became a major question for engineers, when electrical engineering became a thing, the obvious problem was that sending something through lines is always very noisy, and what you get out in the end is corrupted by all sorts of disturbances, reflections at the end of the lines, and so on. And so you needed a piece of equipment that separates the signal from the noise. And these things are called filters. And they became major research question around the Second World War, when sending signals was particularly important. And so initially there were hardware pieces being built that filtered the signal to leave out only certain frequencies. And then the question arose how to optimally design these filters such that certain signals are optimally recovered. And that's where all this theory comes from, that then was studied by Norbert Wiener, who was an early person who proposed this kind of question and then provided some early answers. And then Kalman got famous by figuring out the correct gain for these filters, so how much to separate between your current estimate and the new observation that you've made, how to trade off sticking to your previous guess and using information from the new observation. And that's, of course, exactly what we're doing with this kind of derivation. So here we are back picking up what we did on Tuesday. Quick recap. I did a very abstract lecture, which nevertheless got some reasonably good scores, pointing out that if you're facing a problem where there's a continuous stream of data arriving, then a feature of your inference scheme to separate information, to extract information from this signal, from this data, might be that you would like a local memory, so that the computation has the property that at every time step, the computational overhead is constant and the memory overhead is constant. We found that the structure to impose on your model, on your probabilistic generative model for the data to achieve this is called a Markov chain. So a sequence of states that satisfy this Markov property, so that the probability of the next state given all the previous states is completely described by the previous state, and observations being only locally created. When your model has this property, then in a very abstract fashion, we discovered that inference in this streaming sort of setting amounts to what's called Bayesian filtering. So that's where the filters come in again. That consists of essentially two steps. At least conceptually, we'd like to think of them as two steps. Of course, we could also write them as one equation, that it would be harder to pass. But in principle, we could also do this. But it's easier to think about two steps. One is called predict. We take a step forward in time and predict what the next state will look like given everything we've known so far. And this is encoded by this Chapman-Kolmogorov equation, which is a recursive statement with effectively a convolution mathematically of this Markov kernel, this is sometimes called, with the current belief. Then we do an update. That's the easy part. It's just Bayes' theorem locally applied. And we have a continuously evolving estimate for the current state. That's enough for the online setting. Now, if we at some point are done, and then want to reason about what we actually, now that we're at the end of our time series, know about all the past states, then there is an additional post-processing step, which runs backwards through time, and that's called smoothing. And it, again, is a recursive computation that can be done in linear time in the length of the chain. Now, so far, I've done this in a very abstract way, deliberately, because it allowed us to talk about the algorithmic structures, and we even discovered that there is a really cool way of writing this update in a prefix sum structure so that it can even be parallelized to some degree, and then the inference cost is actually logarithmic in the length of the chain, assuming that we have an unbounded amount of compute available, parallel compute. But so far, these computations they're really not something you can implement on a Turing machine, right? They're just an abstract statement. They involve convolutions and integrals that don't have an explicit form yet. So to get an algorithm, we need to make some assumptions about the explicit form of all of these p's in here. And like I could ask, but it's probably pretty obvious what the assumption is that we're going to make. We'll assume everything is Gaussian, and the relationships between the random variables are linear. If we do this, then we get a base class of problems in which everything is tractable, and these are called Kalman filters, at least for the forward pass. For the backward pass, the algorithm is called the RTS smoother, for Rauchtungsstriebel smoother. So we're going to assume, and I'm going to go through this over the course of several slides, that we have a Markov chain where the initial distribution, so the prior over x1, is a Gaussian. It has some parameters. Let's call them m0 and p0. I've written down the distribution here. Then, every time we take a time step forward, we will assume that the probability distribution for the next state, given the old state, is a Gaussian with a linear relationship between the two variables. This is called a transition model, and this is called a linear Gaussian transition model. And it's customary, actually, so here's something I should point out. In this community that does this kind of stuff, so signal processing largely, but also control engineering and some other related fields, there is an established canonical notation. So when I call this A, that's not a random choice. A is always the transition matrix between states, and Q is always the noise matrix on the so-called on the transition model, or the predictive model. And then locally, we make observations that are also Gaussian with a linear relationship to the latent state, X. And here, the notation is that the model, the so-called emission model, or sometimes also observation model, has a linear transformation that's called H, for whatever reason, and a noise matrix that's called R. And it probably goes back to some original paper by Kalman or something, I assume. Yeah, so those are going to be the assumptions we're going to make. And now we'll see that we'll actually arrive at an algorithm that is completely tractable. And that algorithm we can implement, we can play around with it, we can think about all of its structures. And if you're wondering about the big picture, what we're again gonna build up here is a generic framework for computation in time series or in streaming data or for sequences of data. And of course, you know that there are many sequences out there that are of lots of interest also in like wider AI at the moment. The most important set of sequences probably right now are tokens, strings, right, texts for language models. Another interesting set of states to transition through time in a time series are the pixels of images to simulate video. Right? And the models that we now use these days to make these kind of, to simulate the trajectories of such dynamic systems or to infer something about them, of course, are not linear Gaussian, but they are generalizations of this filter structure that we're exploring here. So what's happening at the moment in the course is we will explore these basic algorithms for a bit to understand how you would get all the functionality you might want from these kind of models and how expensive it is to do this and how to implement it and what kind of data structures. And then after the Pentecost break, I will make one big effort to connect all of deep learning once and for all with this Gaussian framework, and then that's it. And we can suddenly transfer everything we do today to huge big models. Let's see how this works. It's obviously going to be a bit tricky to do this in like 2 lectures, but let's see whether we can sort it out. So these are the assumptions. Any questions about the assumptions before I derive the corresponding algorithm? Yes? Do we assume that the x's can take uncountably many values? So here I have to be careful. We will assume that the state x is a real vector. So that means it's finite in length, at least for our purposes, for the moment, right? So you can think of x literally as a vector that contains, I don't know, let's use a symbol, d dimensions, but each element in that vector is a real number, so it can take any real value, or at least on paper, right? On a machine, of course, it's a floating point number. Yeah. Actually, you could wonder whether the x could be a function itself, and the answer is yes, but let's not get ahead of ourselves because this is just going to be nasty, right? But in principle, yeah, could be some really complicated space. Okay, so now let's do the derivations. We actually have everything. Oh, question. So the question is, what are the shapes of A and Q and R and so on? They are, so the easy answer is they're just the right shape. So, I mean, you can think about it, and obviously it's sort of implicit in this notation, right? So let's say we assume that we have D states, and we make, what's the symbol I haven't used yet? So N is the length of the chain, and let's say we make M observations. It's a bit bad because N and M is so difficult to hear, but so let's say Y. So Y can have a different size than X. That's maybe the important bit, right? So you might have 12 states and 3 observations at each point in time, and then if that's the case, then M is a vector of length 12, P is a matrix of size 12 by 12, it's symmetric positive definite, A is a rectangular matrix of size 12 by 3, and Q A is a quadratic matrix, A is a square matrix of size 12 by 12, Q is also 12 by 12, H is 12 by 3, R is 3 by 3, and so on. So everything kind of just works out, right? We're just mapping between spaces. And yes, we have to assume that the size of the state space stays constant across time, otherwise things get really hairy if we want to do this. And we have to sort of, come down and up again and yeah? Good. So your question is about time as a continuous versus discrete variable. Great. Hold that question until, like, I don't know, 20 minutes from now. We'll get back to that. That's a very important question, yes. But for the moment, I'm assuming that we are in what's called discrete time. So we're getting a countable sequence of observations, right? One after the other, after like fixed time steps. Okay, so with these assumptions, we can now basically go back one slide, read off these equations, and implement them as an actual algorithm. So let's first do the predict step. Up there, I've written down again the assumptions, our strictly linear Gaussian assumptions. This is the Chapman-Kolmogorov equation. It's the thing we need to implement. Now, both of these P's are Gaussians. I've copied over the notation with this A and this Q and M and P. So P here is always a covariance, M is always a mean, A is this transition matrix, Q is the so-called process noise, the covariance of the predictive distribution. And well, this is a product of two Gaussians. Products of two Gaussians are Gaussians. Actually, it's a convolution of a Gaussian with another Gaussian, but whatever. It's still, all these Gaussian properties apply. You can go back to lecture number 3, read off in this big table of properties of Gaussians what this is, and we get that the predictive distribution for the state at time t, given all the previous observations, not the local one, is this Gaussian. So it's a Gaussian distribution over xt with a new mean that is a function of the old mean and a new covariance that is a function of the old covariance plus the process noise. And then there's a name for these quantities. These are called the predictive mean and predictive covariance. You're noticing that I'm using all these like specific terms. That's because there is an entire, actually several entire fields devoted to studying this kind of implementation of these algorithms. And maybe the two most important ones are signal processing and control engineering. Control engineers are very proud people. They are like stand in the history of not just Kalman, but also Wiener and all these cyberneticists. They are the original rocket scientists, right? When people used to say it's not rocket science, the rocket science used to be control engineering. Keeping a rocket actually going straight up is exactly implementing these algorithms, right? And so they have, because they're engineers, they've built these very precise languages that the students in engineering schools learn, and then they have to follow them to the T. So what you get here is like an inkling of this huge developed field. And we're only doing 3 lectures on it. If you wanted to get the full story, you can read some great old books by typically Swedish authors, people like Lennart Jung, thick tomes like this, just studying this class of algorithms for a very long time, how to implement them, efficiently in embedded systems, how to adapt them, how to tune them, and so on and so on and so on. Okay, so this is then called the predictive distribution, and this notation is standard with this minus up there. The minus is supposed to indicate that we haven't seen the local observation yet. We've made a prediction, we've come into the time step, and now we're going to get the observation. So let's do the observation. Remember that the update is just Bayes' rule or Bayes' theorem. So we're just, adding one more observation to our posterior by multiplying our local prior, called the predictive distribution, with a likelihood. The local likelihood is assumed to be Gaussian with this linear relationship, with this transition emission matrix H and observation noise R. And here we are basically calling the dot condition method of our Gaussian class. That means we can just read off how to do updates. And what you see here is the updated mean and covariance of this Gaussian. And if you remember the equations from the earlier parts on regression, these equations might not immediately be obvious to you as exactly this update, but if you fiddle around with them a bit, you will notice that they actually are. So the new mean is the old mean, the predictive mean, M minus, plus a linear map of the observation, where Z is the residual, so it's the difference between what we would have predicted and what we have observed. And then there is this object K, which is very important in this literature. It's called the Kalman gain, and it's called capital K because of Kalman. So what it is it's the term that you would expect in the update for the mean of a Gaussian. It's this gram matrix inverted times the covariance between the observation and the thing that we want to predict, the posterior, the mean of this variable xt. And that involves, linear algebra locally. So let's think about how expensive this is. So that's a linear algebra statement. We're inverting a matrix, but it's a matrix of size, number of observations squared locally. So if we observe locally one number, a scalar, then that matrix is a scalar, even if we observe 1,000,000 of these in a row, right? Because if you go along the timeline, then locally we will always do these updates, but they will always be scalar. So they will have a local constant cost that will then be multiplied linearly with the steps. If we observe locally 100 things, then we need to invert a matrix of size 100 by 100. And of course here, you could still bring all this fancy numerical linear algebra to bear that I've talked about in earlier lectures. It's not gone yet, it's still there. It's now localized in time, but in time, if you observe a lot of things locally, you might still have a big problem. And in fact, there are applications of these frameworks, for example, in the simulation of large-scale systems using partial differential equations, where these matrices are the actual focus of the implementation, where everything is really expensive locally because of, you might observe something like a mesh over some simulated space that has 1,000,000 mesh points, and then that's still very complicated. But typically, you might think here of maybe we observe 20 things, and then it's all good. Okay, so that is given our update, and you see that I've introduced these new variables. That there's a new mean that's called the so-called estimation mean. So we had predictive model, and now we have an estimated model with an estimation mean and an estimation covariance. And they are defined in terms of the Kalman gain K and the observation residual Z. Now we also need this smoothing operation, finally, which involves implementing this smoothing equation. You have rearranged things a bit, but it's still the same terms from the previous slide. Again, everything is Gaussian. we have this, remember what smoothing looks like. We have this thing from the forward pass, from the filter, which is now a Gaussian with these estimated means and covariances. We have this Markov kernel for the transition. That's now a Gaussian with our linear transition model. We have the sort of tail of the recursion. That's going to be the smoothing model. I'll need to talk about that in a second. And then we have this previously predictive model for the there's a typo in the slide, annoying, for the predictive model. So for xt plus 1 given y all the way to t, so this should be a minus here, m minus t plus 1, p minus t plus 1 for the predictive means and covariances. Actually, let me see if I can fix this right away. That's slide 10. How do I quickly find this? Predict, update, smooth again. So it should be corrected by while I do that, you can stare at this so that you get a sense for what's happening here. T, there should be a minus here and a minus there. Let's see if this works. Okay, so in a second you'll hopefully see a minus pop up. Yeah, here, good. And now the rest is correct. There's a minus here. So this will be the distribution that we keep updating. So remember how this algorithm will work. We start initially on the left end of this Markov chain. We go forward in this filtering step, locally always predicting, updating, predicting, updating, predicting, updating. At the very end, we are at the end of the, if there is an end, we're at the end of the Markov chain. And now we initialize the smoother with the last estimated distribution. So the ms at time end, at capital T or big N or whatever, is equal to the m without an s at that time, and the same for p. That initializes our backward pass. And now we can go all the way back doing this equation, where we locally do this smoother update. So that's the derivation. So they always get back Gaussian distributions. Now they have what's called the smoothed mean and the smoothed covariance. You can sort of maybe see that this S notation is a bit less, feels a bit less fundamental than the minus and not minus notation. That's because smoothing is often thought of as something less fundamental. It's this post-processing step that is only relevant if you're thinking of a finite Markov chain that you can then go backwards through. So another way of writing these algorithms would be like this. So here's a piece of like pseudocode to show what's happening. And maybe here I should, let me say two or three things. Anyway, this is basically just a repetition of what we just did, but maybe let me point out some structures. So there is this filter step, so moving forward from left to right through a data set, through a time series with observations, that is effectively a for loop, or we've now already learned it's actually more than a for loop. It's a prefix sum, so a more restrictive structure that even allows speedups, that moves from the left to the right through the chain. And it consists internally at every time step of these first two steps, which are computing predictive distributions, predictive mean m minus and predictive covariance p minus. Then we use the local observation to compute what's called the residual, so the difference between what we have observed and what we thought we would observe, or what we expected to observe. Then we compute this, what in this community is called the innovation covariance. It's also, you might also call it the Gram matrix from our background from Gaussian regression. So it's the covariance of the observation. That's a matrix of size, locally number of observations by number of observations. Then we compute the Kalman gain, which involves a matrix inverse. So that's the expensive bit. Obviously, you do not want to call a matrix.inverse on this S. You want to call some more nicer numerical routine that is more numerically stable, like a Cholesky decomposition or a linalt.solve. And then we multiply this Kalman gain from the left onto the residual, onto the innovation or the residual, update the mean, update the covariance. And this is a short and compact and numerically stable notation for new covariance is old covariance minus outer product of something with a Gram matrix inside. The smoother would then look like this. It's a pass backwards from the right to the left, and it involves locally computing. So what does it involve? Maybe to point out a bit of structure. A, we have to keep in memory all the parameters of the forward pass, so the predictive means and covariances and the estimated means and covariances, the things with the minus and the things without the minus. Then we have to have access to those at the end. So they need to be stored in memory, which means we need linear memory capacity in the length of the Markov chain, which is why this doesn't work in an online setting. And then locally, we compute what's called the smoother gain, G for gain, because this time Kalman is not involved. And this is again involves a matrix inverse of now the size of the states. But maybe one interesting thing about these equations here is that, as you can see, this update does not involve, at least not explicitly involve, the data anymore. So we can do the backward pass without accessing the data source again. This is sometimes important to point out because there are settings where collecting the data itself, making the observation, is actually the expensive bit. It depends on the exact application. For example, if you're simulating a large dynamical system, then accessing the observation might be solving a differential equation. That's an expensive thing to do, and then you don't want to do that anymore, right? Or if later on in the course, our data source will be big neural networks, backward passes through neural networks. We don't want to compute gradients through these networks all the time. We just want to have estimations around. And then this is a nice property of the smoother that it doesn't have to access the data anymore. It just does like a post hoc correction that harmonizes the filter statements with each other, basically by keeping track of surprise that happens later in time. Right? So mentally you can think of this, if you like sort of this anthropomorphized view of the algorithm, you can say the filter is going forward and it knows what it has seen in the past, but it's always like gets surprised by new data. And then you would like to send a message back into the past and sort of say, oh, if only I would have known that this is about to happen, I would have made a different prediction. That's what the smoother does. Right? It sort of comes back from the future and says, oh, some surprising stuff is waiting, and then you need to update a lot. Or maybe it says, actually, everything looks as predicted, and then you don't update at all. And so why do we measure whether there's going to be surprise or not? Well, it's in this line, right? It's the difference between what you thought before you were and what you now actually know that you're at. And so you make a big change. This is what this would look like as a piece of Python code that we're now going to look at together to see this work. Here, maybe the thing to point out, okay, so we literally just translated these equations into obvious Python, right? Even very basic sort of naive style Python. You could think of this as like a little factory, right? So there's a function that produces 3 functions. I give it a set of modeling assumptions called A, Q, H, and R, right? So they are the things that describe this transition model and the observation model. A and Q describe the transition model. H and R describe the update. And then this thing returns 3 functions that we can then use to populate our for loop. Maybe one question you could have is, why have I stopped talking about my beautiful Gaussian class that I've now built with so much work over the last few weeks? I've actually contemplated doing that. We could have a method called filter in our Gaussian class that accesses a subroutine that you could call convolve or predict. They're the same thing. The problem with that is that here, I think it's more important at this time to stress the time series aspect, the for loop aspect, than the fact that everything is Gaussian. I think by now you've accepted that Gaussians are a fundamental concept to use. And so I don't want to be too strict within this Gaussian class. If we do that, we also lose some advantages of this, this beautiful associative scan structure that I would like to set as a homework at some point. And also, on Tuesday, I'm going to start doing some more crazy stuff with Gaussian distributions and filters on nonlinear systems. Things will still stay somewhat Gaussian, but it'll become increasingly forced to use this Gaussian class. And I think at some point it outlives its usefulness. So maybe in some future installments of this class, I will do everything in this one Gaussian class. But here I'm just going to implement these methods. But what you can keep in mind is that whenever we're building a model that takes in a mean and a covariance and returns a mean and a covariance, we're effectively mapping on the space of Gaussians. Right? So you could think of these functions as taking in a Gaussian and returning a Gaussian, taking in a Gaussian and an observation, returning a Gaussian, taking in two Gaussians and returning one Gaussian. Right? A local pair, a tuple of Gaussians, returning an updated Gaussian. I have some code to just sort of show a basic example of how to use a Kalman filter. It's actually on beat-up Jupyter Hub as well, but I'm hosting it locally because I've burned my fingers now, so I'm going to try that again. So what happens in this code is I am loading some trajectory, some basic two-dimensional thing that we can plot, so a curve that moves through time. And I load this from some CSV file, and then I decide to put all these, like all the measurements. So x and y, this is maybe a bad notation. Yeah. So in this x and y are actually x1 and x2. So they are coordinates, or y1 and y2 more precisely. So measurements of the location of something that we'd like to track with our Kalman filter. So now after this, I have a time series in memory that consists of two measurements locally, x1, x2, at n locations across time, where n here is, actually, I don't know. Let me run it, and then we can see. 300, okay? Whatever. So it could also be 3,000 or 30,000. Doesn't matter because we'll have linear runtime, so it's going to be fast anyway. Now I initialize the actual filter. So initializing the filter basically means instantiating a Gaussian class, calling the constructor of a Gaussian class, but I'm making my life simple by sort of writing more sort of bare metal style, just the parameters that describe the model. A is the transition matrix. I'm going to make a very simple assumption of a unit matrix. Q is the process noise. Again, unit matrix with times the scale. I will assume that I actually observe both states, but with noise. That's H and R. And then I need to initialize with an initial prior for the state at time t equals 0, which I set to M0 and P0. Then I define this Kalman filter that I just wrote down. That's the slide that you just saw. And now we can run an actual Kalman filter. So we use this factory to produce three functions: predict, update, smooth. We initialize, we may have a data structure that stores stuff so we can make a plot. And then we run forward. And here I do something slightly non-standard. I do predict steps. And then because I want to show you what the filter does when it doesn't see any data, we just say sometimes in the data set there is just no observation, just a none. And when that happens, then the filter only predicts, and it doesn't update, and it just continues. But when there is data from the sensor coming in, then it updates and stores stuff and moves forward. So now we can run on these 300 data points, and it's pretty much instant because a for loop with 300 steps is not that much. And then I have a little plotting function that I can use to make this plot. So what you see here, and I actually have this also on the slides, so we can look on the slides, is the following. So you wanted legends, so here's a legend. Not sure how much it helps. So the red thing is the actual curve, which we don't know. There's this latent thing that we'd like to know. There's a system that follows some trajectory. Think of a rocket flying towards us. We'd like to know where it is. Now, the blue things are the measurements. So at certain points in time, our whatever radar or sensor tells us where the thing is that we're pointing at. And then you see an orange thing and green ellipses around this. The orange things are the estimated means of the Kalman filter. And you see that they get updated through time. And the green things are, every single one of them is one predictive covariance. So that's your local uncertainty about where the system is. And now what is maybe not so easy to see here is that under this particular model that I've here instantiated, there are actually several time steps in between each measurement. So what happens here is the system gets its first measurement, that's the blue dot. Actually, this is the end, so it starts over there. This is the blue dot initially, we start here. We get the first measurement, we jump there. Actually, we've initialized the system at 0, 0, but it's so uncertain that we don't see that, so it just moves over here after the first, or maybe I think the first measurement is at time step 1, so we just go, boom, jump right over here. And then we stay there for a while, because our transition model doesn't tell us what to do next, so the filter just stays there and waits for the next measurement. But while it waits, it becomes more and more uncertain because the process noise keeps getting added. And so this green ellipsis gets wider and wider and wider and wider until the next measurement comes, and then it jumps to that measurement and becomes uncertain again, and jumps to the next measurement, becomes uncertain again, and so on. And you see it sort of hop around following the trajectory. So, just a second. Maybe that's something you're not particularly happy with, so we'll have to address that, right? One of the things we'd like to fix is maybe that we don't want this sort of sticking around for a while. Well, a first way to fix this, we actually already know how to do. What's missing here? The post-processing step. The smoother. So let's run the smoother. I have the code for that as well. It's here. It's this cell. It's just a backward pass. So we initialize the smoother mean and smoother covariance with the last estimated mean and covariance from the filter run. And then we run a for loop backward through time, call the smooth function from our filtering and smoothing factory at every point in time. We store this stuff, and now we can make a plot, and it looks like this. So on the left is the same plot you just seen before. On the right, you now see what happens after the smoothing step. So the violet points are the smoother means, and the ellipses around them are the smoother covariances. And what you can now see maybe a little bit is that, so first of all, we don't have the filter sticking to one point anymore, because now it has observations from the future that tell it, oh, in the next observation, you're going to be over there. So you should probably start moving that direction, right? And so we get a linear interpolation in this model between these observations. And also, the covariances are now more, maybe more meaningful, right? So they become, the filter now the smoother knows that when I'm at some point in time, it knows when the next observation is going to come. And so it begins to become more confident again as we approach the next observation. And so what you see is that in between observations, the uncertainty goes up and then goes down again as we get towards the next observation. A consistent posterior. Okay, there were questions about this. Beautiful question, so I'm going to repeat it. He says, it looks like in these filtering steps, the covariances are independent of each other. Shouldn't they somehow relate to each other? So now we have to be very careful what exactly we think of independent and dependent, right? So independent is a statement about random variables. And so we are not assuming that the states at every individual time t are independent of each other. What we are assuming is that they are conditionally independent on each other when conditioned on one of the neighbors in between them. Right? So if I have two states, x at t and t plus I, then when I condition on any state in between, they become independent of each other. That's the Markov property. But when I don't have anything in between, they are actually dependent on each other. And the dependence between them is described by the Markov kernel, by this P of Ti given Tj. Now, what we're plotting here, though, are the means and covariances of local Gaussians. So they are, by construction, they're just marginal distributions, right? I'm using the properties of Gaussians that every marginal of a Gaussian, joint Gaussian model is just a Gaussian. So the things I'm plotting are just local Gaussians. So the plotting language here doesn't allow me to talk about covariance yet, the way that I'm doing this here. But it doesn't mean that these random variables are independent under the model. If I wanted to show some covariance, something I would need to do is to draw samples, maybe. That would be one way to show covariance, right? I could draw joint samples from this potential hypotheses for the trajectory of this system. And that's actually possible, but it requires an additional set of methods that we haven't really implemented yet, which, I mean, you're doing sampling this week, so you can think about what that would look like for a filter. The initial model that you might come up with is not going to be the efficient one because it won't have linear time complexity. It turns out that there is a way to draw consistent samples from such models that only works in the backward pass. So you have to finish going through the data set, and then the smoother can actually, as an added step in, you can think of an additional method in here that also drags along a bunch of samples from the last step and keeps updating them. This is called backward sampling. And we're just not going to do it, but you might implement it next week as a homework, or the week after next week or so, or if we can get to it. I will have a whole lecture coming up towards the end of the term when you're all completely loaded up with complicated ideas about deep learning, where I'm going to make the bold claim that randomness is completely pointless and useless. So I'm sort of setting up this big punchline by rarely showing samples. So if you want to follow along, then check how often I'm using random numbers for something. Okay. At this point, I think we should take a break, and I'll sort of spoiler alert, after the break, we're going to spend just a very compact amount of time, because I know not everyone likes the theory, thinking about what these models have to do with these Gaussian models that we've used so far in regression. We'll be back in 5 minutes. Do you have you don't have it? So actually, we go back one slide up. So there was a great question in the break that I briefly want to address before going to the theory. There are several questions now about what's dependent and independent here and how do things relate to each other. And I like them a lot because they highlight how many different dimensionalities and structures are in here. And it took me, when I started working on filters, a long time to understand all these intricacies of how things relate to each other. So you don't have to expect to get this all right away. But this plot is actually maybe richer than you might think. So one observation that I've just heard is someone said, well, it looks like these ellipses, they are all axis aligned. They are all like, right? They are not rotated. They might be stretched, elongated in one way or another, but they are all sort of always aligned with the coordinate axes. And this is not a fundamental property of the Kalman filter at all. That it's a feature or a bug of the model that I've used here, which is maybe the most basic model. You'll remember in the code, I've decided to set, oh, nice, great. So here in this model, I've decided to use a lot of very simple matrices. I'm initializing the prior state, like the state at time 0, with a Gaussian with diagonal covariance, axis-aligned covariance. I am making local observations with axis-aligned covariance. And I'm assuming transitions with axis-aligned noise in Q. And as a result, the entire model only ever gets diagonal matrices added and inverted and multiplied in, and it never becomes covariant. So also the A A is also a diagonal matrix, right? So you can, if you want to, you can do the exercise and convince yourself that as a result, all these matrices will always be completely axis aligned. So they will have no entries on the off diagonal. That's not something we can't change. It's obvious how you change it, right? You can try play around, change any of these matrices in there, and you'll see a much more complicated behavior emerge. Why would anyone ever want to use such a model that is so restrictive? Well, because it makes things very cheap. So if everything is a diagonal matrix, then all the matrices you have to invert in your state space also are diagonal. And then things are fast. If you know, I mean, the way that I've implemented it doesn't get any faster because I'm just calling a linear solve. Question? You mean for smoothing? So here it looks, you're saying, like the ellipses are rotated. That's just an artifact of the plot. So here what you see is a sequence of axis-aligned ellipses overlapping with each other that follow the trajectory of the system, and that looks like they're rotated, but they're not. They're just locally little circles. Actually, not circles, but axis-aligned ellipses that, because they have an alpha value, they overlap, and it creates this visual confusion. Okay, so a little bit of theory. Here, huge warning. There is an insanely complicated theory behind all of this, which we can just about scratch the surface of. And I'm going to do that now with you, with sincere apologies to all the mathematicians in the room, because I'm going to butcher completely some beautiful piece of math. I'm going to highlight some of it, and then we'll just write right over it like the computer scientists that we are. So here's the motivation for it. Remember that Tuesday, I already pointed out that we've actually already encountered one of these Markov processes, the Wiener process. It has this very, very basic structure that you can even implement in like 2 lines of Python that says to go from one time step to the next, we just locally add Gaussian noise. We just keep adding a Gaussian random variable in every time step. If we do that, then we get this random walk behavior. We start at some initial point, and then we just keep adding random numbers. And that's easy to implement. It's also clearly a sum. That's where the motivation for this associative scan with the prefix sum came from. That's literally the archetype of a prefix sum, right? You prefix over here, and then you just keep summing along here. We also remember Einstein, Brownian motion, right? We discovered that when you do that, the expected distance from the initial point after time t is proportional to the square root of the number of time steps. You see this here. This gray line in the background is the square root function. So the region in which we're in grows with the square root of the number of time steps because we're adding independent Gaussian random variables. Okay. And you'll remember that when we did Gaussian process regression, I had this little kernel for the Wiener function. I did this quite naive, maybe, limit process where I said, oh, we can just increase the number of time steps. We'll just have more and more and more. And then you sort of asymptotically converge to this process that looks really rough. And it locally, it looks like Brownian motion, basically, right? And we even found a kernel for it. It was the minimum function. The minimum function between 2 points actually is a positive definite function, and it's the kernel of the Wiener process. But how does this relate to this more direct construction of starting at the left and then adding a Gaussian random variable in every time step? Well, we can actually do this here as well, right? It's just as I decrease the step size, I just have to multiply by a smaller scale that linearly decreases with the width of the steps. So I'm just adding a random variable of variance delta t. I can do this for this plot, and there are still finitely many steps here. But for the Gaussian process, I had this kernel, this covariance function, which actually took in continuous inputs. And we found that there's a continuous limit of this process. But what's the corresponding concept for adding some randomness at every step? I would need a way of talking about adding randomness in an infinitesimal manner. And because you've had a lot of differential calculus, you're sort of thinking, it's just a derivative, right? But it's a really shaky concept to add something random in an infinitesimal manner. So if this were a continuous function, the thing we're talking about would be the derivative, the local instantaneous change. So, but what happens to our local instantaneous change if it's a random process? Well, let's try and do this. So what we are doing when we're taking a finite step here in this process, which you can write as a piece of code, totally fine, nothing goes wrong. We can just say that the state of the system at time t plus finite dt is the state at the time t plus a Gaussian random variable of standard unit variance and zero mean scaled by the time step, delta t. So in this finite time, we can do something like this. We can say, we can compute x of t plus delta t minus x of t dt. And then we see that this is wt. It's this Gaussian random variable, right? So if this weren't a stochastic thing, if it were just a number that we have pre-allocated, then this would look, you probably know where this is going, right? So if I know what wt is, if I then do delta t towards 0, what do I get? A few people should be, just to make sure everyone's following. So okay, some people are nodding. So what am I going to get if I take delta t to 0 and I know what wt is? Nothing random? First term? Or, I don't know, 11th grade school or something? The derivative, yes. You're like, I'm not allowed to say it. This is a trap. This must be a trap. But it is, yeah. So if we knew what like if this were like a non-stochastic relationship, then the thing we're looking for is the derivative. But we're assuming that it's a random object. And it'll be a different one, independently sampled at every single point in time. Now you're realizing I just made this like big setup that I'm not going to talk about randomness. The trick here is not the assumption that something is random. The trick is that the things are independent of each other. How do we think about independence in an infinitesimal sense? We would need something like this. You would like to be able to write something like this. There is a derivative of some probabilistic object, of a probability measure, that somehow describes this instantaneous independent change. But this process will actually be not a differentiable function because it's independent of each other. Right? So that breaks the idea of differentiability. And so what people do is they talk about this object as a weak derivative, as something that only exists when you integrate over it and doesn't exist as an actual object, because if it would, then it would have a different value at every point on the real line. And this corresponding probability measure that's sort of indicated here is called the Wiener measure. And it's a bit of a dangerous object that is only defined when you think about it integrated over it. That's the idea of weak derivatives in calculus, is that they're sort of only defined when they show up as an integration measure. There's a huge, complicated field of math hidden behind this called rough path theory that is actually still quite active. Martin Heirer got a Fields Medal for it a few years ago for studying this field. There's a lot of open questions there of how to do things right and how to even define them properly. But we don't have to deal with that. We'll just leave it out there and say there's some crazy math happening behind the scene. And for us, this is really just a conceptual notion that allows us to talk about our algorithms, and it's connected to the idea of a stochastic differential equation. Who's heard of stochastic differential equations before? A few, I would say 20% of the room, okay? So here is my definition of a stochastic differential equation. It's not a particularly precise one. If you want to read a full detailed introduction, if you don't like listening to the amateur here telling you about this, one book I can very much recommend is this book by, it's on the wrong page now, wrong screen for me, sorry, let me move it up here. By Simo Säke and Arno Solin from Helsinki. Great colleagues, both of them, and they've written this very detailed book that you can just click on and read, and you can see that 311 pages, and they go to great pains to define exactly what I'm talking about very vaguely. Namely, that there are these objects called stochastic differential equations that you can think of as the infinitesimal version of these discrete time processes. They are the object that defines the continuous time limit of the discrete time processes that I've introduced so far. And the notation for them looks like this. We're describing the change of some system in continuous time t as a deterministic change. So that's a function of the state x at time t integrated over time. If this were a general function, this would just be a differential equation. If this f is a matrix, then it's called a linear differential equation, and you've encountered them in your undergraduate classes. And then there's an extra thing that says there is another function, L, that acts on this thing, this Wiener measure. And you should think of this object over here not as something particularly concrete, but as a symbol, as a notation that says we're talking about this infinitesimal object that only really makes sense if we're talking about finite time discretizations. So it's just a notation that allows us to write things compactly, but if we want to have something to operate on and compute on with a computer, we will always have to discretize it eventually. A little bit like for Gaussian processes, I wrote down a kernel, and a kernel is also effectively something abstract that you have to implement on a computer, and it only produces meaningful outputs once you instantiate it, once you actually call it. Think of this as like a lazy description of a complicated process. And here, again, if we assume that L is a linear function, then this whole thing is linear, and we call this a linear time-invariant stochastic differential equation. Why time-invariant? Because f and L do not depend on time. If they would depend on time, we would call it a linear, but not time-invariant stochastic differential equation. Now, it turns out, and that's a completely non-obvious thing to say, that such linear time-invariant stochastic differential equations actually describe uniquely the behavior of a stochastic process that is a Gaussian process. So it is defined by its mean and covariance function, uniquely identified. And that mean function is given by this object, and the covariance function, the kernel, by this object. So at first you see, oh, something complicated is going on. Maybe the most important thing first to realize is there is a direct map from such SDEs to Gaussian processes. That means SDEs, or linear time-invariant stochastic differential equations, are a subset of the space of all Gaussian processes. And what is happening here is that we take what's called a matrix exponential, so it's a generalization of the exponential map to matrices, where f is a matrix now, applied to the initial value. And then the kernel is something that operates similarly with an integral over these functions. And typically these will be hard integrals, and it's not obvious how to do that, but in principle that's the relationship. These are uniquely identified. We can also take these f and l's and map them back to these discrete time systems. And then we need these matrices A and Q, transition matrix and process noise. And here they are. They can also be computed using certain integrals. Now, it turns out that for linear time-invariant systems, where this here is literally this exponential map of some linear transformation of the time, these integrals can be done in closed form by computing a matrix exponential and then doing some fancy math. And people have actually implemented that for you, and I've actually have the corresponding function, which was written by Simo Säke himself here in this Jupyter notebook that you can look at if you like. It's a function that takes in f and l. These are both matrices, rectangular matrices or square matrices, and it then returns A and Q. And how exactly it does that is a bit of a mystery. You have to stare at it for a while, or if you really want to know, you have to read in this book that I just linked. It's in there. It explains exactly how to do that. But you don't need to know. It's just numerical computations of matrix exponentials and then integrals over them. The important thing is, it turns out that there is a continuous time limit of these discrete time systems. It's called a stochastic differential equation. These stochastic differential equations are just a placeholder for Gaussian processes, a special class of Gaussian processes that has the Markov property. These are called Gauss-Markov processes. There is a map that takes you from these linear differential equations, stochastic differential equations, to a discrete time model, and actually also to a Gaussian process. The other way around is a bit harder. You can think about why. I'm not going to spend much time on it, but you can maybe get an intuition for why it's much harder to take a kernel and a mean function and somehow arrive at an SDE. Why is this interesting? Well, it's interesting because it allows us to talk maybe more fundamentally or design more fundamentally systems or describe the behavior of systems. Just like a differential equation is a very powerful model to describe the behavior of a system because you can think instantaneously and locally without the overhead of discretization to describe exactly what you mean is going on. Let's do 2 examples of that. First, here's the very basic example to make sure you're following along. The most trivial, the basic linear time invariant stochastic differential equation is this one, where we set the so-called, so by the way, these 2 terms are called drift and diffusion. The drift is the deterministic part, the diffusion is the stochastic part. It's a motivation from physics. If we set the drift to 0, then there is no deterministic behavior, and the diffusion to something constant, just a scalar quantity, then we're effectively drawing from this Wiener measure. So that's going to be the Wiener process, obviously. And you can check that the transformations work. So our discrete time model will be the matrix exponential of the 0, which is a 1. And the process noise will be, there's a bunch of 1s here, like e to the 0, e to the 0. It's an integral over theta squared dt, so it's just theta squared dt. That means variance grows linearly with time. Standard deviation grows with the square root of time. That's our Brownian motion random walk. What's the corresponding Gaussian process? Well, the mean function is the function that keeps everything constant. Wherever you start, you stay on average. And the covariance is, if you can read up on the previous slide how to do that, there is a 1 in front, and then again an integral from t0 to the minimum of t and t prime over 1s times theta times 1, which is just theta squared. Integrated, we get back our minimum kernel, shifted by this offset that you also already encountered when we talked about the corresponding Gaussian processes. So, okay, the computations work, but that's of course not particularly interesting. Nevertheless, I want to use this opportunity to point out one very basic, but actually also very important property, which is, for which I briefly have to flash the Kalman filter at you again. So remember, to implement a Kalman filter, you do this for loop. Where is it? Sorry, here. That repeatedly does this prediction and update thing. And to do that, we make the prediction, and then we compute a Kalman gain. So if you do this with the Wiener process, then A is the unit matrix, so everything here gets really simple, and Q is just a scalar. And then the Kalman gain is a relatively simple operation that involves basically just the observation noise. And so the gain just checks how much you know so far, how confident you are about the state, and how much information you get from the observation, and then trades them off against each other and makes an update. Now it turns out, there's a bit of theory for that, it's not entirely obvious, that if you run such predict update steps sequentially with constant time steps for a long time, some such Kalman filters asymptotically go into what's called a steady state. So then the Kalman filter, the Kalman gain, k, asymptotically approaches a constant value. That's interesting because when that happens, you don't need to do any linear algebra anymore. You can just implement the Kalman gain once, and then you can just run with it all the time. That speeds up the computation even more. That's really like the most basic case you could achieve. There is some theory for how to construct these steady states. It's also in that book. And for the Wiener process, this very basic class, the limiting predictive covariance that you then approach if the gain is constant is given by this, where you see that there is just a ratio between R and Q, right? R is the observation noise, Q is the process noise. So it's just checking how much information you're losing because you're moving forward through time and how much information you're gaining because you're making an observation. trading them off against each other to compute some kind of signal-to-noise ratio. And the Kalman gain is then given by this constant, it's just a number. And the mean update becomes this. So this is an equation you've seen before. If you replace k with alpha, you're seeing an exponential moving average. So every time you've used an exponential moving average in the past, you've actually used a Kalman filter. You've just used the most basic Kalman filter there is. Why is this interesting? Well, I mean, okay, it just means, okay, I've used an exponential moving average. That means I've used the Kalman filter. Well, I would like you to take this thought back home with you and think about what that actually means for what happens when you're using an exponential moving average. First, over lunch maybe, think about where you're using exponential moving averages. Right? SGD, for example, is an exponential moving average. Right? Maybe you've updated some estimates, maybe you've tracked some things before, you've done several experiments, you've retrained a model after some changes to the data. That's where these exponential moving averages come in. Whenever that happens, you're actually using a Kalman filter. And that Kalman filter doesn't just have a mean, it also has a predictive covariance. And that predictive covariance is now directly tied to the learning rate in your model, to the Kalman gain. But you've now realized that the learning rate is actually the Kalman gain. So you can actually think about what that number is and how you set your learning rate. And suddenly, maybe this insight tells you something about how you set your learning rate. Or if you set your learning rate in a certain way, it tells you something about what you're assuming about the underlying dynamical system that's moving. It's actually quite useful to think about it this way. We'll come back to that at later lectures on the side. Yes? Oh, yeah. This should all be t. This should be mt minus 1, and that's then yt. Yeah, so it's a minus 1 here. But yeah, at this point, it's just a, okay, so this is maybe also the way that people then typically write these equations, where you just overwrite your current estimate in this way. Okay, so another thing we can do with this state space representation, and that maybe actually informs why these exponential moving averages are now suddenly interesting, is that this insight connects these very basic algorithms for tracking stuff with a much more powerful language of these stochastic differential equations. Because now what we can do is we can say, well, maybe I know a bit more about the problem I'm trying to model, and I'm going to express it in terms of, for example, an ordinary differential equation that describes what's going on, plus a little bit of noise, this bit at the back here, or some injection of noise in a particular way to the dynamics of some underlying known system. For example, we could do something like this. We could say, this system, it seems to follow a smooth trajectory, so it should have a derivative, actually. I know that it has a derivative. It looks like a smooth trajectory. Maybe it's a physical system. It's a particle moving with mass. Saying that a particle has mass just means that it has a differentiable trajectory. So let's have a model that says there has to be something called the derivative. The way to do that is to just introduce a second state and say that new state is called the derivative, x and x dot. Now we're tracking two numbers per dimension rather than just one. And we're saying that they evolve according to some ordinary differential equation plus some stochastic bits. And by designing the matrices F and L, we're producing a description of this system. This code, by the way, is also in the Jupyter notebook that I've shown you before, but I'm not going to go back to it. You could just read it off. What does this equation mean here? So here is a matrix F in the deterministic part of the differential equation, the so-called drift. And what it says is, remember that capital X is now this. It contains our state and its derivative. The first row of this equation says the first state is the derivative of the second. That's what it says. Right? This is sometimes called an integrator matrix. So the instantaneous time change of the first state is given by the second state. That's a way of encoding that this is a derivative of the other thing. And then the second row tells us what we think the derivative is doing. If I would put zeros in here in the entire column, then that would mean I'm assuming that the derivative stays constant through time. So if it takes a certain value once, it stays there. And we would get back this model for the derivative that we've just looked at before the break. But I'm going to do something ever so slightly more cunning. I'm going to put this minus lambda in here, which says that I'm assuming that over time, the velocity will go down. A physicist would say I'm imposing friction on the system. So I'm saying the velocity will tend to go back down to 0 if I leave it alone. So lambda could be called a friction coefficient. And by setting lambda to various values, I can make the system very viscous, right? It'll slow down very quickly. I will dampen the system. Or if I set it close to 0, the system will become free. It'll remove friction and move freely. I could actually also put a positive number here, and then the system would do the opposite thing. It would be critically underdamped. It would start to accelerate randomly in some direction. Right? So if you push it, it's like rolling down a hill. If you start moving it once, it gets faster all the time, falling into a potential. This is a free particle moving under friction as a model. And you could think for yourself about what you would change in this equation if you wanted, for example, to impose a potential to keep this thing around. Actually, sorry, no. This is imposing a potential. Yeah, so you can think of this as moving in a quadratic potential. And then I'm saying over here, there's a 0 up here, which is my way of saying it is actually the derivative I'm modeling. If I would put a number here that's non-zero, that would mean I'm adding noise to the thing that is the integral of the derivative, right, the original state, that doesn't affect the derivative itself. And that would break the deterministic relationship between the state and its derivative. So I'm not going to do that because I want to have a system that actually has a meaningful derivative. But I am adding some noise to the derivative. And what that means is that it's not a deterministic system that just slows down and stays, but it actually gets randomly agitated by this Brownian motion. So what I'm building here is physically a model for a particle that sits in a potential. The potential is this minus lambda. It attracts it back to 0. Every time it gets accelerated away from 0, it attracts it back to 0. But then there is some outside Brownian motion that keeps kicking it out of this potential all the time. So it has this non-differentiable path and always wants to go back. This process is, so if there were no no upstate here, if this were just a scalar system, then this is called, does anyone remember from the kernel lectures? It's the Ornstein-Uhlenbeck process. It's a particle bound in a potential, in a thermal potential. And by adding this extra state, I'm getting an integrated Ornstein-Uhlenbeck process. This is sometimes called the Matern process of type 1. And it now gives us a more interesting prediction. So this is a way of making the filter predict what's happening next. You now see that in the same trajectory, this filter starts, it begins to observe that the system has a velocity after the first few measurements. It sort of picks up on that, and then it follows the system around its trajectory. And let's maybe go a little bit here where it speeds up. You see that the system, at this point, it has picked up quite some velocity, and the filter has noticed that it's moving in this direction. And so when it has no observations, in between two observations, it nevertheless tracks the system because it knows that it's probably moving in this direction. But it also gets increasingly uncertain. You see these ellipses grow, right? Because there is this perturbation that we don't know. It's exactly the kind of behavior you want from a tracking system, right? I've lost my target for a moment, so I'm getting a little bit more uncertain, but I'm still keeping track. I'm thinking, well, last time I saw it, it was moving this direction, so let's keep going that direction. And of course, it's literally now just a 4-state system, right? 2 per dimension. You can, of course, make something much more powerful out of this. Play around with this yourself. Think of other ways of encoding more, like a second derivative, for example, to make a system with acceleration that acting under some force. Okay, that will have to suffice for pointing out how to build such models. Next Tuesday, I will spend some time trying to build an actual example, a little bit like what we've done with the Keeling curve for Gaussian processes, but now with a different data set. So we'll come back to that. In preparation for this, I need to point out one more thing before we're done, which is that, as you now see clearly, these models they rise and fall. They're completely dependent on picking good parameters. Right? We need to know how to set lambda in here, and also maybe how to set that number, which I've now cunningly set to 1. Maybe we should be more careful and figure out how to set it to. So intuitively, the number that goes in here tells us how quickly these green ellipses grow. And the number that I put in here tells us how quickly this thing slows down if you don't see anything. If you set this to 0, then it can happen, and you can actually try this yourself with the code, that the filter gets very lost in between. It just shoots off. If you get one bad measurement, it just goes whoop, all the way off screen, which of course might be bad for your sensor. You might not even detect where this bogey is that you're trying to hunt anymore. Right? But if you set it to larger value, then it will just always slow down. It'll see an observation and just go, just get stuck wherever it is. So we need to find a good value in between. How do we do this? With parameter adaptation, in the exact same way that we've done it for Gaussian processes. The only question we're going to have is, when we use the framework from Gaussian process regression to fit hyperparameters, is it still going to be fast and cheap? Or is it going to break this nice linear cost structure that we now have? How did we do hyperparameter adaptation for Gaussian processes? Someone shouted out. Yes? Yes, we maximized the evidence. We computed the likelihood for the model, the marginal likelihood. And now what we need to check is that this is still possible to do Kalman filters without increasing computational cost. And thankfully it is. And this is called the prediction error decomposition. So remember that, so for Gaussian processes we did something like this. We computed the probability for the data under the model, under the parameters. And now we have a model at the moment for the data and the latent state, well, and also the parameters, which is given by whatever our prior for the parameters might be. We can pick it, we can set it to whatever we want to make things convenient, times the probability, the joint probability for the latent state that we don't know and the data that we get to observe. So to see that we can operate, we can compute this thing, this quantity efficiently, what we'll do is we'll first reintroduce x, use the Markov structure, and then marginalize out x again. So let's do that. We've assumed for our Markovian model that the probability for all the x's given theta can be written as this Markov chain, so a product from time 0 to n over these local transition probabilities. And then the local observations are made with this local dependent structure. So yi only depends on xi. Now, if we want to marginalize out all the x's to compute this, we integrate over x here, and we see that we can think of, because of the Markov structure, as a local probability for the ith datum given all the previous data. So from 0 all the way to I minus 1. That already tells us that we can do this computation locally somehow. Well, actually, no, it doesn't quite tell us yet. We can realize that we probably can do that. But we need to know what it looks like for our Kalman filter. So let's first do the proper abstract derivation. This object from up here, we can describe by reintroducing all the xi, then using the Markov property. So we first of all, in the first step, we just use the product rule. So we write this joint distribution as a conditional times xi. We discover that this is something we know how to compute. So this is our predictive distribution that we get from the Chapman-Kolmogorov equation. And then a local observation likelihood. And what we need for, what is the step that's now missing? How do we get from there to there? Do I even change anything? Okay. So the only thing here we use here is that here there's a y, but we know from our assumptions somewhere like a few slides ago that yi given xi is independent of all the other y's, so we can drop the y's. And now we have terms that we know, right? So these are both quantities that show up in our model so far. This is the observation likelihood. That's the Kalman predictive distribution. So we can plug them in. Here is our Gaussian predictive distribution and Kalman predictive distribution. And we can do this integral. It's a Gaussian times a Gaussian. So Gaussian convolution, we know what that integral is. It's this thing. And actually, we can identify the parameters in this Gaussian with things that are already in the Kalman filter notation. So Z, you remember, is this residual observation minus predictive mean. And S is this innovation covariance from the Kalman filter. So these are quantities that we're already computing when the algorithm is running. And the cost of tracking this likelihood is literally 0 because we've already computed them. And if you go back to the slides about associative scans, you'll discover that this associative scan structure actually gives you exactly the right quantities back. It gives you this element, this tuple of 2 elements, and the top element in that tuple is exactly the Kalman estimated distribution without the minus, and the bottom tuple is exactly that number. So this associative scan already computes the things that you'd like to compute. So here's also another picture for this. The situation is just as before for Gaussian processes. There is this sort of Occam's razor thing going on. We get local terms of Gaussian evidences. So to compute the likelihood for the entire data set, given the parameters under this Gauss Markov assumption, that likelihood separates into a product over individual local terms that involve parameters that we already know because we've already computed them in our Kalman filter. And if we want the log likelihood, which is maybe a more convenient object to work with, we take the logarithm of this, so we get a sum over a bunch of numbers that we've already computed. And those numbers, again, contain a fitting term, something that tracks how well we have predicted the data. We want that to be small error. But when we do that, we end up making S large, most likely, and we pay a price for that through this logarithm term because we're making the model uncertain, and being uncertain is not a good thing, right? Because we have to spread out knowledge over a large space. So locally, this gives us this kind of structure, right? There's this penalty for having a large variance and penalty for not predicting the data well with high confidence, and as a result, there's some optimum in between which we will fit. That's actually enough. So you can run gradient descent as a function of theta on this, and then you'll fit a model. In algorithms that actually do this in practice tend to be much more sophisticated. Why? Because they're running on embedded systems very efficiently. So maybe as a final thing to tell you today, engineers who build such systems that, for example, track other targets efficiently, quickly, or the driving assistance systems in cars that watch out through sensors into the street to detect whether you're approaching an obstacle or not. They tend to spend a lot of time tuning parameters using frameworks like this. And so what they typically do is that the Kalman filter is the base object that they work with anyway. It's like they don't even think about it. It's this completely obvious algorithm that just produces a continuously running estimate. And then the effort effectively goes into tuning the parameters of this model. First, by writing down a very carefully designed stochastic differential equation that keeps track of all sorts of things you might know about the setting you're in. And then building very robust adaptive systems that track parameters of the model by effectively following the gradients of this expression with respect to the parameters of the model. So just to remind you, where are the parameters here? So Z is a function of the predictive mean, which involves H, and the predictive mean involves A and Q, and the predictive covariance, which again involves H and R and A and Q, so they're all in there. And you can take derivatives of this expression with respect to A and Q and R and H and tune them. But what you typically don't want to do is just do gradient descent, because that might be unstable, it might push you in weird directions that you can't come out of anymore. So you want to constrain this space very efficiently, and then you want to think about how quickly you want to adapt your parameters. because you have a time series that changes through time, right? So you're assuming that probably these parameters might change through time as well, typically, right, for many, many settings. But if you adapt too quickly, then you can get fooled by some few observations locally. If you adapt too slowly, then your system will be, slothy and won't adapt quickly. So there are actually routines that try to estimate how quickly the system is changing and then control the adaptation of the parameters. And this quickly gets very complicated. Many algorithms that do control effectively are all about solving this kind of problem, efficiently tuning the parameters of a filter. Okay, there's one more question, but I first want to wrap up and then see if there's one more question. This is the second out of 3 lectures about Gauss-Markov models, filtering and smoothing, Bayesian filtering and smoothing. We've now encountered the base class of state space models, of models that track a dynamical system through time. They're called Kalman filters. They have linear compute cost in the number of time steps, cubic worst case complexity in the size of the state space. They are connected to Gaussian process models. In fact, they are, if they are linear time invariant, a subclass of all Gaussian processes. And that means they are typically described through this language of stochastic differential equations, which we can use to encode salient physical knowledge about dynamical systems. If you've worked with differential equations before and you like differential equations, then you now have suddenly a very powerful language to describe the behavior of a system you would like to track, no matter what the system is, and you can control very carefully the computational cost and memory cost associated with it. You can also track the parameters of such systems by effectively tuning the hyperparameters of the Kalman filter. Next Tuesday, we'll do the last lecture on this, where I will try to, in just 90 minutes, build an example Kalman filter for a complicated dynamical system. And we will quickly discover that such systems typically tend to follow nonlinear dynamics. And that will mean that we'll have to think about how to incorporate nonlinear dynamics into this linear system. That's going to be one entire new class of algorithms, which I'll quickly introduce. And then we'll use it to solve some ever so slightly realistic example application. Any immediate questions? I guess everyone wants to leave for lunch anyway. If not, then thank you very much. See you next Tuesday.